Let's turn to a very important example of chemical equilibrium, which is the interactions of many molecules with water to change the ratio of ionized water. So this is either adding protons, H pluses, or OH minuses to the water. Generally the protons occur as H3O plus, but we'll ignore this in much of what follows. Now water itself dissociates. The dissociation rate is pretty small, but some fraction of bulk water consists of protons and OH minus ions. So the equilibrium constant for the dissociation of water is shown here, and it is in fact 1 part in 10 to the minus 14. So the forward rate for the dissociation is actually very small. Since water is a pure substance, its activity by definition is 1 when it's in the normal liquid state. And therefore one can rewrite this definition of the equilibrium constant for the dissociation of water as follows. Of course, all divided by 1. Now, this means that in neutral water, no acid or base added, the population of H plus must equal the population of O minus, and that therefore means that, for example, the fraction of protons is 10 to the minus 7, because the product of that with the concentration or activity of OH minus has to be 10 to the minus 14. We define a useful quantity, which is the pH, as minus the logarithm base 10 of the activity of protons. And so you see therefore that in neutral water the pH is 7, as is probably well known to all of those of you who've had to look after swimming pools. Now, many acids do not dissociate fully when you add them to water. They partially dissociate, and the acid dissociation constant, which is shown here as K sub A, is given by the ratio of the dissociated products, which I'm going to show as H plus X minus all over HX, can be understood particularly easily for the case of conjugate acid-base pairs. Let me give you an example of a conjugate acid-base pair. For example, sulfuric acid, H2SO4, the molecule, can dissociate into HSO4 minus plus H plus. In this reaction, HSO4 minus is referred to as the conjugate base of the acid H2SO4. So returning to this definition of equilibrium constant, if we take logarithms of every term, base 10, and multiply everything through by minus 1, and then rearrange, this of course is just the pH. This quantity here we will define as the pKa by analogy with pH, we end up with this equation here. And then we're going to call X minus here the activity of the base over the activity of the acid. This equation is called the Henderson-Hasselbalch equation, and it shows how the pH of a weak acid is controlled by dissociation of that acid. The next slide shows the pH as a function of base added to a weakly dissociating acid with a pKa of around about 4.5. The pKa, by definition, is the pH value at which the ratio of base to acid is 1, so the logarithm is therefore 0. So at this point, pKa equals pH. So what you see is that near the pKa, the pH changes very little. So let's just sketch this out. This is equivalence in terms of moles of OH minus added to the weakly dissociating acid. Here is the pH of the weakly dissociating acid. The pKa here was at around about 4.5. And what you see is that in this range here, the pH changes relatively little as significant amounts of base are added to the solution. This is an example of buffering by a weakly dissociating acid, and many compounds form excellent buffers. Blood, for example, is an excellent buffer, and the pH is changed relatively little by fairly large amounts of acid or base added to blood.